Glendale's Verdugo Mountains are a geologic entity. The diverse accumulation of various rock types and geological formations that compose the vast landscape is breathtaking. These mountains are a part of the transverse range system that spreads across Southern California. This transverse range system is a complex geological puzzle. But how did this come to be? What is the story behind these vast mountain ranges? The honor students at Glendale Community College set out to discover exactly how these pieces fit together and why they spread apart in the first place. This is Unearthing a Local History, Geological Analysis at Glendale Community College and Beyond. At the base of the Verdugo Mountains lies vast recreational areas. The first step in uncovering the secrets that lie within this mountainous mosaic was collecting rock samples. Local parks were chosen for this task. Brand Park in Glendale and Stowe Canyon Park in Burbank were chosen for the metamorphized limestones that exist within the numerous hiking trails. The samples from these locations would be compared to the data collected from similar rock types decades ago, 60 miles east of Glendale and the Jurupa Valley of California. The challenge with investigating mountains in the transverse range system comes from their composition. Most of these mountains are primarily made of gneiss, a common metamorphic rock. The lack of distinction between each mountain's composition makes the geologic puzzle more difficult to piece together. The presence of unique rock types, like the metamorphized limestones within these mountains, aids in differentiating and correlating the various pieces. The students hypothesized that the Brand and Stowe Canyon Park areas were once connected with Jurupa Hills, and that a strike-slip offset caused them to separate. If the samples of rare rock from these local parks contain minerals that were reported in the Jurupa Hills findings, then they would be able to link the two samples together and validate their hypothesis. The students were determined to unearth the geological history buried beneath the surface.
Our professor, Dr. James Sheed, has since then collected samples from the Brand and Stowe Canyon trails and walked through the making of thin sections. After studying under a polarizing microscope, these thin sections made it possible to view our samples in a new way at the California Institute of Technology.
This group of curious students embarked on a journey to the California Institute of Technology to get a closer look at the geological concepts they had studied all semester. At Caltech, they utilized two types of equipment to analyze their samples. The first one, a scanning electron microscope, or SEM, uses a beam of high-energy electrons to scan the surface of the sample. This process creates signals such as secondary electrons and backscattered electrons. These signals are then converted into electrical signals that display a high-resolution visual image on the monitor. This image allows for the analysis of the rock samples. Here is Dr. Chi Ma, a lab director in the Division of Geological and Planetary Sciences at Caltech, explaining the loading of carbon-coated thin sections into the vacuum chamber of the SEM microscope and how the electron beam will scan the sample.
Electrons from your specimen atoms. Okay, now it's vented. We pull the door open. Okay, now we are going to load the sample. Okay. So actually this is north, this is the south. Mm-hmm. This is X direction, electron beam scanning along X, moving down the Y. So we put the picture there, load sample like this, image look like this. Mm-hmm. So alright, so this is a little bit perfect. Okay, now we place it. Now we're going to count down.
Once he loads the thin section into the machine, he needs to focus the electron beams in order to get a workable, high-resolution image of the sample. He shows the tedious process of focusing such a small beam of electrons on such a thin sample. Once focused, the machine starts scanning the sample and converting the signals into an image. The image is in grayscale with varying tones of gray corresponding to different minerals. The data can now be interpreted with the help of the researchers at Caltech. The students also worked with Paul Asmo, a professor of geology and geochemistry at Caltech. Here he is conducting the analysis of feldspar from one of the samples using the X-rays ejected from the mineral's surface.
It's kind of small, and it's not very homogeneous looking in backscatter, right? But it was once a nice rectangular prism of an intermediate feldspar, right?
Once the samples are analyzed by the X-ray diffractometer and interpreted with the help of the researchers, data regarding minerals and their compositions are collected from various mineral grains in the thin section. This data is then downloaded and researched by the students to get a clearer picture of each of their samples. Once the students have researched the mineral composition of their samples, they use the other piece of equipment available at the Caltech lab, an electron probe microanalysis, or EPMA. This machine also uses electrons to create interactions with the sample, but these interactions emit X-rays that are unique to each element. An energy dispersive X-ray spectrometer measures these X-rays and identifies the elements and their concentrations in the sample with incredible accuracy. The operation of this EPMA is similar to that of the SEM. A beam of electrons is directed at the sample and the resulting image needs to be focused. Once the beam is focused, a high-quality image is produced, which allows distinguishing the different minerals present within the rock. The data that the EPMA produces is very specific. The X-rays can reveal the elemental composition of each mineral. This accurate analysis is instrumental in determining if the samples from Brand Park and Stowe Canyon were once connected with the previously studied samples from the Jurupa Hills.
The technology provided to us by Caltech was the only way that we could compare these metamorphosed limestone to the separated mountain blocks. Though it was complicated at first, Paul and she walked us through the entire process, and with the help of our professor, we were able to gather useful data to help in our research.
The students took data from both the SEM and EPMA sessions and concluded that the minerals in their samples were similar to the ones reported from the Jurupa Hills, suggesting the mountain ranges were once connected and bringing them one step closer to proving their hypothesis of the existence of the strike-slip offset.
Even though there is more to be done to prove our hypothesis, these lab sessions proved so much for our research. We were now able to take a solid step forward and now have the necessary information to continue our exploration into the world of geology.
This 75-million-year-old geologic puzzle has not been completely solved, but the research conducted by the honors students at Glendale Community College with the help of Caltech was able to put just a few pieces together and benefit future endeavors to reveal this geologic mystery.